Today's lesson is 4.8 Quadratic Functions. What will we learn today? To graph a quadratic function and to use the graph to estimate a value. A new vocabulary word, quadratic function. Quadratic function can be described as two different ways. Our definition is a function in which the greatest power of the variable is 2. And the second thing, it's a graph. Its graph is U-shaped, opening upward or downward. Quadratic functions. A quadratic function can be written in the form y equals a times x squared plus b times x plus c, where a does not equal 0. The graph of a quadratic function is called a parabola. The graph opens upward if the coefficient of the variable is positive, downward if it is negative. So for example, if we were to have y is equal to 2x squared plus 3x plus 4, because the 2 is positive, our parabola would be positive, and just like that. If we had y equals negative 2x squared plus 3x plus 4, because of the negative, our parabola would be facing downward. Example number 1, graph y equals x squared. So the first thing we want to do here is to make a table. And we are going to make a table. And because this is squared, I'm going to use 5 different values. So I'm going to have my input x, my output y. So let's go with 1, negative 1, sorry, 0, 1, 2, 3. And let's plug that in. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. So now I want to plot the order points. So this order point is negative 1, 1. So negative 1, 1 is right there. 0, 0, which is our origin. 1, 1, right there. 2, 4, right there. And 3, 9, right there. Once we've plotted our points, we connect the points with a smooth curve. So I'm going to do this here, but I can obviously tell that it's also going to continue on the left-hand side. So this is what a quadratic function looks like. And it's a positive parabola. Again, my invisible one, positive 1, it's positive, so it goes upward. Example number 2, graph equals negative x squared plus 4. Because my variable squared is negative, I know I should have or end up with a graph of a parabola facing downward. So let's go ahead and create our table. This table I'm going to do a little bit different from the prior one. I'm going to include the rule. So I have my x, my rule, negative x squared plus 4, and my output. I'm going to choose negative 2, negative 1, 0, 1, and 2. Always using 5 when we're doing quadratic functions. Excuse me. So let's go ahead and plug in negative 2 squared plus 4. So negative 2 squared is 4. Don't forget the negative on the outside. So negative 4 plus 4 is 0. Negative 1 squared plus 4. Negative 1 squared is 1. Or negative 1 plus 4 is going to be 3. And then negative 0 squared plus 4. 0 squared is 0. So negative 0 plus 4 is 4. Negative 1 squared plus 4. Again, 1 squared is 1. It becomes negative. negative 1 plus 4 is 3. And then last but not least, negative, in parentheses, 2 plus 4. 2 squared is 4, or negative 4 plus 4, which is 0. So let's plot these points. My first point is going to be negative 2, 0. So negative 2, 0 is right there. Negative 1, 3. Negative 1, 3. 0, 4. Right there. 1, 3. 1, 3. Notice it's starting to come back down. 2, 0. And there is our graph. Our quadratic function, and like I mentioned before, it's negative because I have negative x squared. Example number 3, real world problem. The function d is equal to 4 times t squared represents the distance d in feet that a race car will travel over t seconds with a constant acceleration of 8 feet per second. Graph the function. That's the first thing we're doing. Then use the graph to find how much time it will take for the race car to travel 200 feet. So we're going to start off with the table. And we want to use positive values because obviously you can't go negative seconds. So we'll use t, our seconds. I'm going to plug in my rule, 4 times t squared. And that's going to give me my output of my distance. I'll pick 5 different numbers. 1, 2, 3, 4, 5. And now I'm going to substitute each of my inputs into my rule. So we'll start with 4 times 1 squared. 1 squared is 1. So 4 times 1, 4. 4 times 2 squared. 2 squared is 4. So 4 times 4, 16. 4 times 3 squared. 3 squared is 9. 9 times 4, 36. 4 times 4 squared. 4 squared is 16. 16 times 4, 64. That was a mistake. 4 times 5 squared. 5 squared is 25. 25 times 4, 100. So my ordered pairs, 1, 4, 2, 16, 3, 36. And again, I need these in order to graph. This would be the first part. It says to graph the function. The second part is how much time will it take for the race car to travel 200 feet. Excuse me. So down here is going to be my time, my t, and my d, or my distance, is going to be my y-axis. So I see that I go from on the distance from 4 all the way to 100, and I want to check 200. So what I'm going to do is I'm going to go ahead and label these by, we can go, let's say every second one is 50. So I'll go 50, 100, and that's going to be too much in between. Or not enough in between. Let's go 25. 25, 50, 75. So every 2, I'm going up by 25. 100, 125, 150, 175, and 200 will be about right there. Okay, so let's start plotting. Let's make this 1, 2, 3, 4, 5, 6, 7, 8. 1, 4. 1, 4 is going to be pretty low down here. 2, 16. A little bit higher. 3, 36. And we'll put it about there. 4, 64. About there. 5, 100. Right at that point. And I'm going to graph this. I'm going to start at the origin. And let me keep going, actually. So I'm going to try to guesstimate, just keep going straight. And now to answer the second part, use the graph to find how much time it will take for the race car to travel 200 feet. So it's going to be an estimate. So let me go here and then down. Looks like it's going to take about 7 seconds. So let me try that. Let me plug in 7. Let's go 4 times 7 squared. 7 squared is 49. 49 times 4. Let me check that in my calculator. That's going to equal 196. So I can say how much time will it take for the race car to travel 200 feet? It's actually going to be more than 7 seconds. So part B, or 2, will be more than 7 seconds. Our last example, example 4, the function h equals 0.66 times d squared represents the distance d in miles you can see from a height of h feet. Graph this function. First thing I'm doing, I'm going to graph. Then use the graph to estimate how far you can see from a hot air balloon 1,000 feet in the air. Okay. So how far can we see from up to 1,000 feet? So again, we're going to use a table. My input is going to be d. My rho 0.66 times d squared, and then my height. Okay. Now, I'm going to need to reach up to 1,000 feet. That's my height. So I don't want to go 1, 2, 3, 4, because that will take me forever. So what I'm going to do is I'm going to go ahead and go by tens. Let's go 10, 20, 30, 40, 50, 60. See how that works out. And I'm using base 10, which is going to make it easier for me to multiply also in my head. 0 times 66 times 10 squared. So 10 squared is 100. 100 times 0.66 is 66. 0.66 times 20 squared. 20 squared is 400. 400 times 0.66, 264. 0.66 times 30 squared, that's 900. 900 times 0.66 is 594. Getting closer. 0.66 times 40 squared. 40 squared is 1,600. 1,600 times 66 is going to be 1,056. Well, that takes us over the 100 feet, right? So I don't need the 50, 60. So let's look at a graph, and we're going to go, because we're going up to 1,000. Let's go ahead and every box we're going to make it 100. So there you go, 200, 400, 600. Let me mark mine. Point 800, 1,000, 1,200, 1,400, 1,600. I don't need to go any further than that. Excuse me. So we'll go 10, 20, 30, 40. Now let's plot our points. 10 is going to be 66, which is going to be about right there. 20 is 264, about there. 30 is 594, almost to 600. And 40 is 1,056. Again, this is the part First part where it says to graph. And so now that we have the graph, that's part one. Now we can see, then use the graph to estimate how far you could see from the hot air balloon 1,000 feet in the air. One thing I forgot to write down also, my labels. In this case, distance is my X, because that's what's changing. That's my input. And height is my Y. So 1,000 feet, go across, and as you can tell, it's not quite 40, which we know because 40 would be 1,056. So how far can you see from a hot air balloon at 1,000 feet, or from a hot air balloon 1,000 feet up the air? You can see about, we'll say 39, and we're talking feet, or miles, sorry, distance in miles, 39 miles.